Thank you. And thank you, Tommaso, and the rest of the organizers for having me here. I'm very happy to be here presenting these works that coincidentally appeared today on Archive. And so the talk is really about subradiance, but more generically, it is about multi-level systems and how we can take advantage of multi-level of atoms with a more complex internal level structure to maybe create interesting state for quantum applications. And so the motivation to study multi-level systems in our case comes from the nice experiments that are running at GILA, like the optical lattice clock experiment of the group of Junji, where here there is a 3D lattice, and in each of these spots there is one atom, which at first can be thought of as a two-level system. And each of these atoms effectively is like a little clock with a frequency given by the energy difference between the ground and the excited states. But this is a bit of a more the dream of a theorist. In reality, these atoms are strontium-87 atoms, which have a very large nuclear spin of 9.5. So this two-level system actually looks more like this, with a 10-fold degeneracy of both the ground and the excited states. And of course, this becomes very complicated, but it is important to take this into account when you start looking at effects that can affect the accuracy of the clock. And so one of them is spontaneous emission, where an excitation spontaneously emits a photon, and this can lead to loss of contrast and coherence in the clock. But if you have a multi-level system, this excitation can decay to different ground states, which will change the dynamics. And the other important effect is dipolar interaction between the different atoms, where an atom basically goes down from an excited state to a ground state, and the photon emitted is reabsorbed by another atom, and then that one goes up to the excited state. Again, for multi-level systems, this becomes more complicated because the excitation can go down to different ground states, and the ground atom can go up to different excited states. But these dipolar interactions can also be useful because when you have this type of interactions, the effective decay rate of the excitations is modified. A famous example is subradiance, but here I'm going to talk about the opposite, the other effect, which is subradiance, where if you have an ensemble of interacting atoms, the effective decay rate of the atoms can be suppressed because of these interactions. And you will see that the physical basis of this can be understood in terms of quantum interference of different decay processes. Now, here specifically, I'm going to talk about dark states, which you can see as a sort of extreme case of this phenomenon where the decay rate totally vanishes. Yeah? And for those who have seen it before, a famous example is the decay state, the decay antisymmetric state, which is dark when you have in the limit where two atoms are very close to each other compared to the wavelength of the transition. So now this type of dark or subradiant states can be very interesting for quantum applications because of their very long coherence times. For example, for quantum metrology, as I was telling you before, but also for other things like quantum information or quantum simulation. And recently there have been quite a lot of theoretical proposals for generating subradiant states and for different applications of them. This is a little selection of mine. And I should say that most of these works deal with two-level systems, and only few of them, more recent ones, are starting to study multi-level systems. In comparison, however, there are relatively few experiments still that have observed subradiant states. And the reason for this is that engineering subradiant states can be very challenging. And one of the difficulties of this is that often proposals for generating subradiant states require the atoms to be very close to each other in order to enhance the dipolar interactions between them, in particular close compared to the wavelength of the transition. And this can be very hard to engineer in most cases. Another difficulty is these states are generally very sensitive to the geometry of the system and also to other details, and that these systems are generally very hard to prepare because of their weak coupling to the electromagnetic field. Can you hear me, or is it fine? Yeah, it goes a bit up and down. Okay, I'm gonna stay. Okay, so here in this work, we propose a new approach for generating subradiant states, which we think can circumvent some of these issues, and it is based on three things: on having multi-level atoms, using fermion statistics, and having 2 atoms per lattice site. So let me go through this in more detail. So we are thinking of having an optical lattice, for example, in 2D, 3D, or whatever geometry you want. 2 atoms per lattice site. I'm going to put here. Filled with 2 atoms per lattice site. And we are going to assume that the atoms are very tightly trapped, so that the atoms occupy only the motional ground state of the lattice, and such that tunneling between different sites is suppressed. Now, each atom is going to be a multi-level fermion with an internal structure like this, from a degenerate ground state with an angular momentum of Fg, and a degenerate excited state with an angular momentum Fe. Right? As I was mentioning before, these atoms interact with each other via dipolar interactions, both between different sites and also on the same site. And the interactions can involve all possible transitions between all these levels. And the final ingredient is that because of fermion statistics, there are certain decay channels of the excitations that are blocked by Pauli exclusion. For example, here in this example, the red atom, by the way, I'm using red for excited and blue for ground. The red atom cannot decay where the blue atom is, because that's occupied, and these are fermions. So this is blocked. And this is going to help us create dark states. So in order to describe this system, we use a master equation approach with a Hamiltonian part for coherent exchanges between excitations, and a Lindbladian part for incoherent ones, which includes both single particle spontaneous decay and correlated or cooperative decay. Now, this is basically a flip-flop interaction, but with multiple internal levels. And it is written in terms of these D- and D+ operators, which are Hermitian conjugates of each other. And they can be seen as multi-level raising and lowering operators defined like this. Now, for a 2-level system, this would be just a Pauli minus operator, and the D+ a Pauli plus operator. But for the multi-level system, it's a sum over all possible decay channels weighted by the Klebs-Gordon coefficient of the transition. All right. And now the interactions depend on these coefficients, R and I, that depend on the distance and orientation between the 2 atoms, and on the polarizations, Q and Q prime, of the involved transitions. And the only thing I want to say about this is that these interactions are long range, which I guess qualifies this work for this workshop. But the good or the bad news, depending on the perspective, is that the results are very independent of the form of these coefficients, so I'm not going to talk about them anymore. This will be to get into the workshop. So, okay, of this system, let's look for dark states. Yeah, and a dark state mathematically is defined as an eigenstate of the Hamiltonian, which makes the limit part like this. And the key for the whole work is really the realization that there is a sufficient condition for this system to fulfill this, which is given by this thing here. Now, to see why this is the case, so the state D has to be a 0 eigenstate of this D- operator, which is like the multi-level lowering operator. And to see this, you can just look at the master equation, where the D- operator appears here, here, and here. And if you insert a state that fulfills this here, you just get a big 0. You get 0 decay and 0 energy. And the nice thing is that for 2-level systems, or for having 1 particle per lattice site, you cannot fulfill this condition. But for multi-level systems with 2 or more particles per lattice site, you can. So this gives rise to new types of dark states. And physically, the basis for this is quantum interaction between different processes. So a state D, to be dark, has to, all the decay channels with the same polarization and the same final state have to interfere destructively for it to be a dark state. I'm going to show you an example here. For the most simple case, where both the ground and the excited state have an angular momentum of 1/2. So the internal level structure looks like this. And it turns out that for this system, this particular superposition of states is a dark state. Okay? To see this, we can go through the possible decay channels. So first of all, the ones with sigma plus or sigma minus polarization are simply blocked by Pauli exclusion, because of the presence of the other atom. Because of this, there is only one possible decay channel for each, which is this one, both with the same polarization. And now this superposition is precisely chosen in such a way that those two contributions cancel destructively. So overall, this makes this state a dark state. And this can be generalized for a general internal level structure like this, where both ground and excited states have an angular momentum of F. And we find that for general F, there is always a dark state that's right in this way, or here is an example of it. You don't need to look at this. And there are two ways of seeing why this is a dark state. One is quantum interference, as I was telling you before. Yeah, from that point of view, for example, the decay of this state here, of this atom here, is cancelled by the decay of this other state here. And the decay of this one here is cancelled by this other one, for example. Yeah, you can go through the math, and this is what is happening, what is going on. But there is actually a simpler way of looking at this, which is in terms of the total angular momentum of the two particles. So the F1 and F2 would be the angular momenta of particle 1 and particle 2 on the same lattice site. And it turns out that this state is actually just an eigenstate of the total angular momentum for angular momentum 0 and projection 0. And to see why this is the case, we can just go through the possible decay channels of this state. And to remind you, so if a state emits a photon, the total angular momentum can only change by 0 or plus minus 1. So there are only two possible states to which this thing can decay, to F0 or F1. But the transition from F0 to F0 is forbidden, like in usual atomic physics. And for the one with F1, what happens is that for identical particles, the state with total angular momentum 1 is symmetric under exchange. And because these are fermions, we need it to be antisymmetric. So this state doesn't exist for fermions, so there are no decay channels for this, and this is why this is a dark state. Another relevant internal level structure is this one, where you have angular momentum F in the ground and F plus 1 in the excited state. And in this case, we find actually many more dark states. There are a bunch of them. And you can write it in this way, but again, you can see them more easily by looking at the total angular momentum. And you see that actually all the states with the maximal total angular momentum, so the opposite from before, so in this case it's 2F plus 1, all these states are dark. And to see why, we can go again through the possible decay channels, which are 2F plus 1 going to 2F plus 2 plus 1 or plus 0. Yeah. But when the atoms decay, both atoms are in the ground state, so the total angular momentum is 2 times F. Yeah. By are too far, do not exist. Yeah. So this leaves the last one, 2F. And here we can use the same argument as before, and one can show that this state is symmetric under exchange, so it's not a valid state for fermions. All right, so here's the little summary of the single site case. So 2 atoms on a single site. I've shown you that there is always one dark state for this type of internal level structure, and there are all these dark states with maximal total angular momentum for this other level structure. And just let me mention that for the other relevant case, with F going to F minus 1, there are no dark states. And this is because there are too many decay channels always to decay, so it cannot be cancelled out. Okay, so this was for one single site. Now let's go back to the case of multiple sites. And for this, imagine you have some product state where some sites are in a ground state with both atoms in a ground state, and the other sites are in some of the single site dark states that I showed before, like this. Well, it turns out that now the dark states fulfill this dark state condition of the beginning just by definition, and the ground states fulfill it too because they cannot decay anywhere. They are already in the ground state. So overall, this state fulfills this dark state condition and makes it a dark state. So any state that you can write in this way is a dark state. Yeah? And it has very interesting properties. First of all, it is independent of the geometry of the lattice. Yeah? I didn't say anything about it. In particular, it doesn't require very short distances, for example. Then it can support a very large number of excitations, up to 1 excitation per lattice site, which is not very typical subradiance states. And last thing is that all these states have zero energy shift. Yeah, they have the same energy, which makes them interesting, for example, for quantum metrology or for perhaps engineering interesting entangled states. Okay, so this is nice, but how can we prepare this state? Well, it turns out that if we just shine on a laser resonant with the ground to excited transition, there is no coupling to the dark state. So the Hamiltonian corresponding to this has zero matrix elements between any ground state and any dark state. Mathematically, the reason is that the Hamiltonian can be written in terms of these d plus and minus operators, which when you sandwich it in between G and D makes it vanish. So instead, what we propose is to use a Raman excitation scheme where we couple the ground and excited states off resonantly through an intermediate transition. And in this case, the effective Hamiltonian that you get has this effective Rabi coupling, which now has a different structure from before. And so this means that this Hamiltonian cannot be written in terms of these operators anymore, and in general. And so you can get a non-vanishing matrix element between ground and excited state. So in this way, you can excite the dark state starting from a ground state. And to see this, here is a little example. Again, for the simple case of angular momentum 1/2, ground and excited states. And here, we start with the two atoms in the ground state. We shine on these Raman lasers, and you can see that the dark state in blue gets excited. But at the same time, this dark state couples to other states, to the double excited state, EE, here. This is the gray line. And this state itself decays to other states, and so everything becomes a bit of a mess. So we have excited the dark state, but also other things. So we would like to have only the dark state. And to do that, we can simply use the quantum Zeno effect by using a very small Rabi frequency compared to the decay of the transition. The effect of this is basically that it's kind of a very quick projection of the wave function, which results in basically almost no population in the states that decay much faster than the driving. Yeah. And here's an example of this. This is for a much smaller Rabi frequency compared to before. And here you can see very high contrast oscillations between ground and excited state, which is what we wanted, with almost no population in the other. And you can generalize this, in principle, to whatever internal level structure and dark state you wanna prepare. And here's an example for the other case, for the case that I was saying about before, with at the beginning with a total angular momentum of 9/2. And here we start instead with a ground state like this, with the atoms on opposing ends of the Zeeman sublevels. And you can think of preparing this, for example, by optical pumping. We shine on the Raman lasers, and we again coherently excite the dark state. Except in this case, we don't reach 100% there, because on the way, we excite other ground states as well. Yeah, for example, this one, and others. But in principle, this is still coherent. And yeah, so in the time that I have left, I would like to discuss some application. Yeah, yeah, of course. Well, it depends on what you want to do with it. If you want to, I mean, if you believe that this is happening after, well, in this case, not so much, but in this case, you just stop the dynamics here, and yeah. Oh, well, so if you want to prepare 100% in the dark state, yeah, you would probably have to project and do some post-selection, I guess. If you are fine with having a superposition of dark and ground states, for quantum metrology maybe, then that's all you have to do. So it depends on what the aim is. Yeah, there may be some other way of preparing 100%. I just haven't studied here. Also, this is a bit of an extreme case. This is perhaps not the one you would be starting with. So there are more simple dark states to excite. This was just perhaps one of the hardest ones. Any other thing? So let me discuss some possible implementations using alkaline earth atoms. For example, ytterbium-171 or strontium-87, the one that I mentioned at the beginning, which have nuclear spins 1/2 and 9/2 respectively. And the nice thing about alkaline earth atoms is that they have a unique electronic ground state, the 1s0 state, which makes the problem easier. And typically, people use a lot for quantum metrology and stuff the clock transition to the 3p0 state, which is very long-lived. But let's say if you want to see something that extends the lifetime of a state, using this right now would be, I mean, it's going to be hard to see something that lives longer than the lifetime of this already. So we are thinking of possible implementations using a faster decaying transition, like the 3p1 here. And we have discussed with experimentalists, and there are a couple of different states that one could think of using for preparing the state for the Raman excitation scheme, as I said before. And in any case, the nuclear spin, the non-vanishing nuclear spin, leads to a degeneracy of all these states. So for example, for ytterbium, it would look like this, like the example that I was using throughout, with 1/2 and 1/2. And to finish, let me discuss some experimental limits that we anticipate for the lifetime of the dark states, because of course nothing is going to live forever. So one of the things is collisions that I didn't talk about yet. Collisions between the two atoms on the same lattice site can lead to mixing between dark and non-dark states. And to be honest, this is a bit of an unknown yet as to how strong this effect is going to be. But what we can say for now is that because the dark states are eigenstates of the total angular momentum, and collisions conserve angular momentum, we expect the dark states to be approximate collisional eigenstates as long as the short-range part of the interactions doesn't play too much of a significant role. But this has to be analyzed in more detail. The other thing is non-vanishing magnetic fields that can lift the degeneracy between the different Zeeman sublevels and again induce mixing between the dark and non-dark states. And however, if the detuning is small enough, small compared to the line width of the transition, then again the Zeno effect can help us and reduce a bit the effect of this by inducing an effective decay rate that scales only quadratically with this. And finally, I assume that the atoms motional band on the ground state, but of course it's an approximation. And in principle, be non-vanishing decay to a higher motional band. And in the case where the atoms are tightly trapped, one can show that in this paper it's shown that the decay to the next excited band is given by this with the long decay parameter eta squared, where eta is basically the ratio between the width of the wave packet, of the wave function, and the lattice wavelength. And so that's it. So the main message that I wanted to convey to you is that multi-level systems provide new possibilities to create interesting states, in particular here dark states. And here the dark states are based on a combination of multi-level, fermion statistics, and having 2 particles per lattice site. And they have interesting properties. They are independent of the lattice geometry. They can support a high number of excitations, and I've shown you how one could, in principle, coherently prepare them. And I talked a bit about the application at the beginning, but let me highlight 2 things. So one thing is that one can think of using now faster decaying transitions for applications where you need long coherence times, because effectively you are prolonging the lifetime of those transitions. And this can open new possibilities for doing things. And the other thing is that these states, because they all have the same energy, they don't have any dipolar shifts. So this can be very interesting for optical lattice clock experiments, where the dipolar interactions eventually will pose a fundamental problem on a fundamental limit on the accuracy of clocks. And the last thing is that, well, we hope to go now beyond this and perhaps including other effects and make these perhaps a many-body interacting system. Let's see. So please suggest ideas. So thank you.
So at the end, you mentioned